Hey, in today's discussion, we're going to be talking about work and what work actually means. Work can mean several different things in an everyday sense. It could mean something like I go to work, right, to make money, or I'm working on my car. But in physics, in our class that we're looking at today, work has a very specific meaning. Okay? Work is the ability to transfer energy from one point to another point. Okay? That's what work is. And we have an equation for work. It's applying a force to an object, and if that object moves a certain distance, then we have work done. So let's take a little bit closer look at this. Work is equal to force times distance. So we said force is the ability to transfer energy from one point to another. And how are you going to transfer energy from point A to point B? Well, you do that by applying a force. And if you apply a force and the object moves, then like I said, we have work done. So let's take a look at some of our units for these things here. For force, we should know by now that force is measured in newtons, distance is measured in meters, and work, that's a new unit to us. That is going to be J, which is joules, Joules. J, or joules, right? Joules, or J for short, represent the units for work. Our force needs to be in newtons, our distance needs to be in meters, and work is a newton meter. We're joules, or J. So let's take a look at an example for work. Let's say that we had a box. We wanted to move this box. Let's say that we're trying to push the box, right? We're trying to push this box. If we apply a force to this box, right, this is going to be some force, and if that object moves some distance, right, we're going to move it from here, which is point A, we're going to move it to this position over here, which we'll call it B. We're moving that box. We're making it go from point A to point B, right? We're applying a force, it moves a distance, we are doing work. Now, a couple of things to keep in mind. Notice that the distance is in this direction, right? Distance is in this direction. Force is in this direction. So the force and the distance that the object moves is parallel. The force is parallel to the distance that the object moves. A little total screen. Okay, sorry about that. The distance and the force are parallel to each other. So when we look at this, right, we look at work is equal to force times distance. These two things must be parallel. They're parallel to each other. So force and distance need to be parallel to each other for any work to be done. Okay? So let's take a look at this equation. We like using our triangle. So if we were to put this in a triangle, We would put work up here in the upper portion of the triangle. Force would be in the lower left hand. Distance would be in the lower right hand. And so we have our triangle for work, force, and distance. Work is equal to force times distance. Force is equal to work over distance. And then distance is equal to work divided by force. So that's our triangle here. That's our triangle if we're trying to figure out work. And the important thing is that force and distance must be parallel to each other. So let's take a look at a couple of examples, right? We've already looked at one where we have a person pushing a box, right? We're moving it horizontally here. The force and distance are parallel to each other. Now let's take a look at a box, and let's say that this box is going to be lifted. And the way that we're going to do that is we're going to use a pulley. So here's a pulley up here. We're going to pull this rope down here. So if we were to pull this rope or this string in this direction, the force, remember the string is holding on to it, so the force is in this direction. So here's our force pulling in an upward direction. What's the distance that this object moves? Well, think about it. If the force is pulling it up in this direction, the distance that the box moves is going to be vertical. So what do you notice about the distance and the force? The distance and the force are parallel to each other. Just like in this example, the distance and force were parallel to each other. So we have work here. We have work being done here because they're parallel to each other. Let's take a look at another example, one that can be confusing at times. Let's say that we have a box and somebody is carrying a box. They're carrying a box across the floor. So if we're carrying the box across the floor, the distance that the box moves is like this, right? We're going to move and we're going to walk this direction. So that means the box was here and it's going to end up at this point here. Okay. Now, think about this. What direction is the force on that box? If I'm holding the box up, I'm not pushing the box forward, I'm holding the box from underneath. So if I'm holding the box from underneath, what direction is that force? That force from my hands is in this upward direction. So I'm holding the box up, right, as I walk across the floor. So if you'll notice, the force is in an upward direction. The distance that the box moves is horizontal. Notice these two are not parallel to each other. They're perpendicular to each other. So even though you may get tired from carrying this box across the floor, there is no work done here, right? There is no work done here because the force and the distance are not parallel to each other. So in a physics sense, there is no work done. Let's take a look at one more example. Let's say that we have a box, giant box, and we want to try to push this box. We're trying to push this box, but this box does not move, and we're pushing, we're applying a big force to this box. Let's say we're applying a force, but let's say that it doesn't go anywhere. The distance is zero. There is no distance. It does not move. Right? We can't get this thing to move. So if the box does not move, distance is zero. Even though we're applying a force to it, right? You may be pushing as hard as you possibly can, but it doesn't move anywhere. Think about this. If you push on the outside of the school and you try to get it to move, you're not ever going to be able to move the school just by pushing on it. So you may get tired, you may apply a gigantic force to it, but if your distance is zero, no work, right? There's no work here. Think about this. Think about it in terms of the equation, right? Work is equal to force times distance. Well, if distance is 0 and we plug in a 0 here, right? 0 times anything is going to make the answer come out to be 0. So work is 0. There's no work done here in a physics sense. You may get tired. You may be applying a force, but if it doesn't move, there's no work done. So let's review those one more time. Is there work done here? Yes. There's work done because the force and the box actually moves, so the force and the distance are parallel to each other. Here, the box is being raised up, the distance and the force are parallel to each other, so work is done here. Notice that, yes, you're applying a force and it is moving, but the distance and the force are not parallel to each other, they're perpendicular, so no work is done. And then if we look at our final example, yes, you may be applying a force to something that's really, really big, and we can't get it to move. So if it doesn't move, there's no work. No work. All right. The other thing that I wanted to talk about in this little section here is machines. Okay, machines. There's two types of machines. There's a simple machine and there's a compound machine. Simple machines just have one single motion. So let's take a look at a couple of simple machines. So if you look here, we have 1, 2, 3, 4, 5, 6 different types of simple machines. An inclined plane, a wedge, like an axe, a lever, like a hammer, wheel and axle, a screw, and a pulley. Here's that pulley there. Simple machines have a single motion. So for an inclined plane, you go up or down, right? Single direction. For a wedge, one motion. Simple machines do not decrease the amount of work. Simple machines make things easier, but they do not decrease the work. Work always stays the same. That is important to remember. Work always stays the same. It may be easier, but work stays the same. And so what happens is an example like this. If we were to talk about an inclined plane, let's take a look at that. An inclined plane is a pretty simple example that we can look at. Let's say that we had a mountain, right? Here's a mountain. We're going to climb this mountain. So if you were to climb this mountain and you went straight up this mountain, right? You tried to go straight up this mountain. You would be doing work. You're applying a force, your body is applying a force to yourself, and you're moving in the same direction. So your force and your distance that you're moving is in an upward direction. That would be tough if you're trying to climb a mountain that's just straight up. How can we make that easier? We can use a simple machine, which is an inclined plane. So let's take a look at that. If we were to add an inclined plane, right? If we made a trail and we made this inclined plane right? Now, if we followed this trail, right, all the way up to the top, did we change how much work we do? No, because we're still having to do the same amount of work. Something happened. What happened? We had to increase the distance. So the force that we felt that we had to apply, the force decreased, but the distance had to increase. So remember our equation. Work is force times distance. So what did we have to do? We decreased the force. It made it feel like it was easier, right? It felt like it was easier, that means we're decreasing the force on our bodies, right? We don't have to apply as much of a force. But what had to happen was that distance had to increase. So force may decrease and distance increases. That just has to happen. So because you're decreasing one, the other increases. So as force goes down, distance goes up. So that means work is going to stay the same. So simple machines cause you to go a larger distance by decreasing force. So it makes it seem easier because force is decreasing, but distance is increasing. So in all, work always stays the same. So a compound machine is simply just one that has two or more simple machines together. So you may have a pulley and you may have an inclined plane, you may have a screw, different things like that. If they're combined together, those are called compound machines. And I think that should do it. Right? We talked about work, what work is, we kind of defined work, and we talked about machines. Okay, so we will continue on from there in another lesson. Good luck.